HRI's Global 1230 Consistent Standard Project Committee, HRI's VRF Compliance Committee, and HRI's Global VRF Standards Committee. So you see, Richie still works for HRI. We just got back in to pay for him. Richie has a Master's of Business Administration degree from Imperial College in London and a Bachelor of Science degree in Engineering from Virginia Tech. So Richie, it's all yours.
Great. Thank you for that introduction, Henry. Much appreciated. And yes, good evening to everyone in India. And I hope you're all keeping safe and sound during the ongoing pandemic. Let's go ahead and dive right into the global VRF standard presentation. So this is a boilerplate disclaimer from ISHRAE indicating the general purpose of this informational webinar and ensuring the protection of its views, which may be different from those of the speakers and the contents of this presentation. All right, so this is the overall outline for today's presentation. First, we're going to take a broader look at the standard activity and understand the reasons behind the development of this global standard. Next, we'll review the current status of this activity and where things stand as of today. We will then take a deeper dive into the key standard provisions, more specifically talking about the scope and coverage for the standard, the rating conditions for both cooling and heating. We'll also take a dive into the performance metrics which are going to be included in the standard. And then there are a couple of very important issues which will be covered. The first being, how do we make sure that the field versus lab performance for VRF equipment is as close as possible to each other? And then the other major topic will be the introduction of the performance mapping approach for VRF equipment for both cooling and heating. And subsequently, we're going to cover some other notable test procedure provisions, such as how are we going to deal with sound ratings for VRF equipment in this standard? And then what are we doing to help facilitate more effective and accurate building modeling and simulation, which seems to be taking a massive uptick in the activity all around the world. And then we'll basically try to wrap up the presentation with showing, what is the intended path to adoption for this global standard and the overall timeline as to when we expect this global standard to be in play on a global level. So that's a quick overview. We'll move on to the next slide, and I'll take a broader look, or present to you rather a broader look on the standard itself. So the preliminary discussions on this overall activity, date all the way back to Q1 of 2018, when members of ASHRAE, Eurovent, and HRI came together to agree on the development of a global test procedure and rating method for VRF equipment. And one of the aims for this effort was to eventually enable the harmonization of test procedures and standard requirements across the different parts of the world, and which would basically help minimize the unnecessary deviations which exist as of today in the different regional standards. Moreover, and looking at it from another lens, we have seen in the past few years that we as an entire global community is stepping up the fight against climate change. And this is all justifiable. Now, there are countries and regions with existing energy efficiency and application and appliance standard programs, which are making these MEPS and energy savings levels even more aggressive and higher. But we've also seen certain countries and regions without any prior energy efficiency programs or appliance standards in place, and they're quickly trying to get these programs in place as soon as possible. And both these types of countries and regions are going to benefit from a globally intended standard, such as that for VRF equipment. And this is also going to help minimize the duplication of resources. It's also going to promote higher energy efficiency savings. It's going to cut a lot of testing cost and also bring in the best minds from around the world to help address a lot of the common issues which are being faced in the VRF industry today. Now, another important item to note is that there are regions and countries today which may be bound to develop and use their own national standard. I mean, India may be one of those regions or countries. And we understand that in such cases, the intention is to provide with a standard which has been vetted by a global community such that it can be used in the overall development process and referencing for your own national standard. This could possibly help to significantly reduce, the reinventing of wheel, which may be happening, in different parts of the world. The standard development team, and this is where I think I want to just focus on the right-hand side. The overall committee and the development team for this global standard has been, pretty much very hard at work over the past couple of years. Despite of COVID-19, there were several committees and subcommittees which met very regularly via web conferencing. And a lot of credit goes to Henry and his team to ensuring the continuity of the operations as well as this activity such that it doesn't fall into a slow pace because of the pandemic. Further, I also want to go over the construct of the global standard working group or the committees. So, we've got a full committee for the global standard, which includes stakeholders, labs, as well as representatives from associations from around the world. But we have three very major active subcommittees under this main committee. The first subcommittee is the lab subcommittee, which is focused on establishing the lab-based requirements in the standard. Then we do have a data efficiency and descriptors subcommittee, which is focusing on performance metrics, calculation methodologies, what sort of requirements need to be put in to ensure, accurate and effective ratings, and so forth. And then we also have another subcommittee which is focused on ensuring that the title, purpose, and scope of this global standard is well represented from the intention or the interest of the VRF community, as well as the fact that it's broad enough that it will include systems and equipment which are sold in different parts of the world. All right, then moving on to the next slide. We will basically first cover the overall scope of the standard. At present, the Global Standard Committee has agreed that the scope of the standard needs to encompass all VRF air-cooled systems which are greater than 12 kilowatts in terms of cooling capacity. Which basically means that residential VRF systems less than 12 kilowatts are not included in this first version of the standard. In addition, as I mentioned, the scope is targeting air-cooled VRF systems, so we are not including water-cooled VRF systems at this time, but that will be definitely up for consideration in the next revision cycle. Another point to note in this scope is that we understand that there are different requirements and deviations which need to be put in based on specific regions. When we talk about, let's say, the climate in in one part of the world, and we look at it and compare it with the climate of another part of the world, that can instigate or support the reasoning for having different requirements to cater to both sides of the world. And therefore, keeping that in mind, you may see certain deviations which have been put in such that we can accommodate the individual country or region requirements in this overall global standard. Okay, now then we'll move on to the next slide, which covers the current status of where things are as of today from the development perspective. There are some things which have been, or items I would say, which have been completed in this draft standard, such as the title, purpose, and scope. You saw the scope already in the previous slide. We've also covered some definitions, which usually takes a good amount of time in any standard development process, is to go over definitions and to get everybody to agree on some of the granular and minute things. We've also completed the test procedures for cooling and heating for VRF equipment in the standard. And there are now several items which have been drafted, but they're still under review by this committee. First being the tested conditions, and I'll go over these rating conditions or rated conditions in the subsequent slides. We're also currently looking into how to address defrost for VRF equipment. And how to address heat recovery test. So basically to see how, the cooling as well as the heating operation from the same VRF system is going to be best accounted for from a testing perspective. We're also looking into how to add in the tolerances and uncertainty levels for VRF equipment. There are certain energy descriptors, which I will go over in some of the slides, and some of the next subsequent slides, which have been drafted but still under review. And then there are instruction requirements. What do we need from manufacturers to effectively complete a VRF test? There are a lot of instructions. Some might be public, in the manufacturer's literature, but there are some which are confidential in nature, and those have to be handled through a different platform. There are a few other things which have to be developed, and the Global Standard Committee is going to get to it as soon as possible. First being how the marking and the labeling is going to work for VRF equipment which are in compliance or rated in accordance with this global standard. We'll also look at what are going to be the publication requirements for ratings. I mean, what is it that is going to be the minimum level of publication as per this global standard? And again, a very important item, which I've got a couple of slides on, which is the controls verification procedure. Okay, moving on to the next slide. All right, so here are the rating conditions which have been agreed upon by the Global Standard Committee. And let me go over the cooling side first, which is on the left-hand side. You've got the indoor room conditions. You've got a 27 degrees Celsius dry bulb and a 19 degrees Celsius wet bulb, which seems to be pretty much in alignment with most of the international standards and regional standards for that matter. There are some discussions which are ongoing about whether we need to even reduce this indoor dry bulb temperature from 27 degrees Celsius to something which, is usually what you see in the houses, which may be 21 degrees or 22 degrees Celsius, or even 23. But I think at this point of time for the first revision cycle, and knowing the amount of effort which will be required for anyone to comply with this standard, it was agreed that maybe it may be best to keep it at 27 degrees Celsius dry bulb. Subsequently, we look at the outdoor ambient temperature, and this becomes important because, well, every region has a different take on what the outdoor ambient needs to be. Uh, we looked at the various regional VRF standards as they stand today. We looked at HRI 1230, which is the US-based VRF standard. We looked at EN 14825, which happens to be the European-based VRF standard. We also looked at the JIS 8616, which is the Japanese standard for VRF, as well as the Chinese standard for VRF, which is pretty much in alignment with the ISO standard. And it was quite obvious that every standard had their own cooling load line. Cooling load line is basically what you see in the brackets out here. And subsequently, we realized that one of the first challenges that we'll have to overcome is how do we harmonize and integrate a load line for cooling, which everybody in the entire world can live with. And at that point, the European 14825 load line, which is again what you see in the brackets out here, was accepted for several reasons. The primary reason, of course, being that it's a straightforward as well as a linear load line. And the linear load line is going to be essential for performance mapping, which we will cover in the couple of slides from here on, which was also being added to the global VRF standard. Again, the other thing being that this load line is very similar to the US load line. I think it's a matter of few percentage points. So it wouldn't be a whole lot of retesting burden. And it also sort of is in tune with the Japanese standards, it's more in specifically 8616 in regards to what they would end up using for a load line. The outdoor ambient temperatures, which have been noted out here in the second row, are 35 degrees Celsius, 30 degrees Celsius, 25, and 20 degrees Celsius. These are also in alignment with what we see in EN 14825. And more specifically, these will represent the full load as well as the part load operation of a VRF equipment. Now, these set of conditions would apply to what we say the ASHRAE 169 climate zones 1 through 8, which is mentioned in the first part of this row. For climate zone 0, which is basically a hot and humid temperature profile, and these are the profiles that you may end up seeing more in the Middle East, such as Kuwait. There was a request to add in a separate set of conditions, which was going to be having a higher outdoor ambient for full load, which is shown in the third row of this table. And then subsequently, the 35 and the 29 degrees Celsius are also in alignment with what regions such as Middle East and specific countries within Middle East are looking at for adoption in their respective standard. Now, we understand that there are going to be other countries and regions which may want to have a different outdoor ambient testing temperature other than what you're seeing out here in this particular table. And we can go ahead and either add those additional testing conditions as optional, such that we are able to accommodate the specific requirements from any region. But beyond that, there is also an alternative approach, which is the energy performance mapping. And the performance mapping will enable, someone who's testing in accordance with this particular test procedure to determine what the efficiency and the rating needs to be at a different condition other than what you're seeing out here. And again, I'll go over that in the subsequent slides. Now, on the other hand, heating. I know heating is not a major uh, of major particular interest when it comes to a region such as India or any other region which may fall closer to the climate zone zero. But I think at the same time, it's important to just look at what is being done on the heating side of things. Um, the indoor dry bulb and the wet bulb temperatures are 20 degrees Celsius and 15 degrees Celsius, respectively. And on the outdoor side, we are going to have a full load and a part load rating condition from, and there's a load line for heating as well, which is shown in this particular cell of the table, in where you will basically go all the way up to 88%, where the corresponding outdoor ambient temperature of -7 degrees Celsius. And you will go as low as 15% of operation in the part load mode, with a corresponding temperature of 12 degrees Celsius. There are some additional rating points which have been added for heating, one being TOI. This is the outdoor temperature, which is declared by the manufacturer, beyond which there cannot be any heating capacity that can be provided. So it's basically the ultimate, bottom of the floor. And that needs to be sort of certified and declared by the manufacturer. Beyond that, we also have the T bivalent. It's basically the temperature condition for heating beyond which the system will require supplemental heating. That needs to be given, as part of declaration by the manufacturer when complying with the standard. And then we also have an optional point, which is, ultra heating point. It's at -15 degrees Celsius. It may be more prevalent and relevant rather in regions which are extremely cold in nature. But I think, we'll basically skip on that one for now for the purpose of this presentation. All right, so let's move on to the next slide. Here, we're going to take a look at what sort of energy performance metrics or energy efficiency performance metrics are being used or thought about to be included in the test procedure or the global standard. Now, the Global Standard Committee understood that there cannot be a single efficiency metric which can realistically be applied to all parts of the world. There are too many climate zone variations which will impact the full load and the part load operation. Therefore, a bin method is being adopted to support seasonal efficiency calculations. There are several bins which have been extracted or rather copied from various regional standards as well as ISO standards, and they're going to be added as part of an addendum in the global VRF standard, such that the user of the standard can then use a bin set which is most appropriate to the user's region. At the moment, we've got 2 bins which have been taken from the ISO 16358 standard, and this is for cooling. And then we've got 3 bins which are in EN 14825, and this is for heating, which have been added into the addendum. But this is not the complete set. We understand that there will be additional bins which we will need to add based on the request coming in from different regions with their different temperature profiles. So as I understand, in India, we are looking at ICER to be the preferred metric for use for various HVAC equipment. Therefore, that particular metric, as well as the corresponding bin sets, can be added into this particular global VRF standard. As for the current set of metrics, we are planning on adding APF, which is the annual performance factor, as well as EER, which is the energy efficiency ratio, and IER, which is the integrated energy efficiency ratio, and COP as well as SCOP, looking at it from a heating standpoint. These four metrics are going to have to be included in the global standard. In addition to that, there will be calculation methodologies and some examples provided as to how to accurately calculate these metrics. But again, beyond that, as I mentioned, if there are regional requirements for performance metrics, we can definitely have those included in the document or the standard. The other thing to note over here is that the committee's intention is to try and harmonize the test procedure requirements between all the different regions as much as possible, such that we can agree upon how the capacity values and the power input values are generated. And once we have an agreement on these measurements and the measurement methods, then the data can be used effectively in different form and format, based on bins values as well as weighting factors, to basically come up with the most pertinent efficiency metric value for that particular region. So for example, if you were to just agree on, let's say, how to generate the capacity and the power input for a particular VRF system, which may be sold in either US or Europe, then as long as we can agree upon what those capacity values and power input values are, then it's just a matter of calculation to come to what the European calculation methodology might be versus what the US calculation methodology might be, and then eventually share, or at least have the final ER or the RER values be verified and eventually published in these two different regions. So anyway, still a lot of work yet to be done in putting the framework out in the global standard with respect to the efficiency metrics, but at least this is the direction that the committee is planning on taking in order to be accepting as well as accommodating to customized or rather the specific requirements, but at the same time also trying to harmonize those requirements on the test procedure as well as rating method standpoint. Okay, so now we're going to take a dive into perhaps an important item which we get to hear about quite a bit these days, and which is how do we best address the performance that we get from a lab versus the performance that we're actually seeing with an installed system in the field, and how do we make sure that those two performance of those two different approaches or installations are as close to each other as possible. So basically making the lab testing be more representative of actual field conditions than what we are using today. This is a topic which has been brought up at the same time in different parts of the world. In the US, we recently went through a regulatory process to revise the VRF standard as well as the energy conservation standards. And this happened to be one of the hot topics which needed to be addressed in the global standard, such that we can try to make the ratings for the VRF equipment be more representative of what's happening out there in the field. And I think there are some subsequent or discussions which are happening in parallel in Europe. Certain regions have also raised similar concerns. And therefore, in this global standard, we have embarked upon adding some requirements which are going to get us there, which is to minimize that gap between the lab performance as well as the field performance. The first thing that we've added is the airflow restriction. So, and this is on the indoor side. So the indoor airflow for both ducted as well as non-ducted VRF equipment are going to be capped off at 247 cubic meter per hour per kilowatt. So you're not able to go beyond these airflow levels during testing. And this was, of course, after reviewing, what would be the normal airflows that you would see in the field for a typical VRF operation. Now, as I mentioned in one of my previous slides, that there might be deviations based on different regional requirements. This is the first example of that deviation, in where for the US and Canadian-based products, basically, there is going to be an SHR limitation, which is sensible heat ratio limitation, that has been added for the full load point, which is the 100% load point for cooling, as well as one of the part load points, which is the 74% load point for cooling. And I'm just going to basically go back and show you the rating condition. Basically, it's for these two particular points in where we have added an SHR limitation for cooling. And what this does is that it ensures that there's going to be a minimum level of latent capacity which will be added or observed during, a typical VRF test. And beyond that, the ratings that are going to come out from this global standard for US-based products are going to reflect a typical level of dehumidification that the system needs to be conducting. And this dehumidification becomes an important topic, especially for cities, on the coastal regions or coastal side of the countries, as well as regions which have very high humidity levels. It may be a big deal, like say, if we talk about Bombay or Mumbai, but maybe not as much as when we're talking about Delhi, where the climate is typically, dry in nature. And so to that point, the US regulatory process, which we went through just about a couple of years ago, the NGOs, as well as the utility companies, which are power providers, as well as manufacturers, agreed that the VRF ratings in the US have to represent some level of dehumidification. And that's why we've put an SHR cap. The SHR cap is basically 0.82 for 100%, which is 82% sensible heat ratio for the 100% load point. And then it's 85% or 0.85 for the 74% load point. But again, for regions which are outside of US and Canada, I think the intention is to tackle the airflow side of things with an airflow limitation, which is 247 cubic meters per hour per kilowatt. Now, beyond that, we've also added a requirement on the part load side in where, let's say for your lowest part load condition, which is 21%, you need to have at least half of the indoor units be shut off. And the reason for doing so is because this is what we're going to see in the field. If your load requirement is basically quarter of the full load, then you should be shutting off some of your indoor units. And this is not really how things are really done all around today. And I think that will be a good step forward to address this overall issue, as I talked about, which is field versus lab. We've also added in some stringent requirements pertaining to the manufacturer's installation instructions. So as I mentioned, there are some confidential instructions which need to be provided from the manufacturer side. There are some public information which can be used through manufacturer's literature in order to accurately and effectively conduct a VRF test. And both of these sets, have been outlined or listed in this global standard, as in what are the minimum level of instructions which need to be provided. And those instructions, of course, have to be, met and used during testing as a whole. And another massive or rather big change that we're adding in to the global standard is the combination requirements. So what sort of indoor units are you going to use in combination with the outdoor unit, such that that overall combination is more representative of what really gets installed in the field. If we're basically going ahead and testing a combination which will never install in the field, then the overall testing method and the rating method becomes very less effective. And so to this point, we can come up with all prescriptive type of requirements, of trying to hone in to make the combinations more representative of what we use in the field. But at the end, we realized that there was always some level of gamification or loopholes which would then exist. And therefore, we've kind of expanded the overall combination requirements to basically any combination which is sold in the field uh, is then basically included in the scope of the standard. So basically, it can be used for testing and rating in accordance with the standard. This will significantly reduce any potential gamification which could be used, which could be done, any potential loopholes which could exist. It's basically we're opening the entire standard up to thousands and thousands of combinations which could potentially exist in the field between outdoor unit as well as indoor unit. Now, of course, from a manufacturer standpoint as well as a design engineer standpoint, that just sounds way too cumbersome. But we have added in certain provisions in the global standard such that the use of modeling tools, simulation tools, which is basically what manufacturers are doing today to some extent. We just have to basically expand the breadth of the simulation tools and modeling tools which are used internally to develop ratings. That rating simulation tool will basically can be used and will be used for the purpose of coming up with ratings in accordance with this test procedure. And that particular rating tool or the modeling tool which the manufacturers are using, that would have to just get verified and sort of approved through the means of this test procedure. And there are going to be some provisions which will be added in there. So again, a big change, but at the same time, it's being done in order to protect the interest of the end consumer or the user, such that the end user and consumer is basically getting the most accurate and precise ratings for VRF equipment when in compliance with this test procedure. Okay, the other item, and just want to see how we're doing on time. Okay, so the other item that we've added in is pertaining to the global VRF test procedure requirements. Is the control verification procedure, or in short, CVP. As I mentioned, the whole lab versus field discussion or conundrum, that can be best addressed if before a steady state test, so during a steady state test for VRF equipment, we try to lock down the compressor speed, we try to lock on the expansion valve settings, we try to lock on the outdoor fan speed. And we do all of these three things and beyond for a reason, so that we can get a repeatable test result, we can get a reproducible test result, and we can get a representative test result. But the thing is that how are we sure that the settings for compressor speed, the fan speed, the expansion valves which are being used, are they really what you would end up seeing in the field, or are they something which are an anomaly, just so that you can get the best ratings out there in the lab, right? And so therefore, the committee realized that we can address this issue by adding what we call a controls verification procedure, because the system controls for VRF equipment are basically the heart of the system. Controls do a lot of really the magic in regards to the flow of refrigerant to the indoor units, between indoor units and outdoor units, as well as basically trying to tackle other various important parameters. And so if we can verify whether the controls are behaving, in a lab as they would in the field, then we basically have tried to address a lot of the major issues. And therefore, before we run a steady state test, we will run a pre-steady state procedure, which is the CVP, in where we leave the entire system sort of in its native state, without having any compressor speeds locked out, without locking the outdoor fan speeds and the expansion valves. We basically just let that system be in the test chamber, and all we are going to modulate is the test chamber temperature. So basically your outdoor ambient temperature, and see how the various parameters of that particular system behave. And once we basically get a range, or rather I would say an operation range for those critical parameters, then that range can then be carried into the steady state test, and that range will basically become your boundaries, such that if you were to lock in your compressor speed, your compressor speed settings cannot go beyond the range that you had observed during the CVP when the system was in its native state, without any external touching really from the lab personnel or the manufacturer for that matter. In this way, we basically try to hone in as much as possible on how the system would really perform on its own in the field. Now, as for what are the critical parameters, these are compressor speed, outdoor fan speed, the outdoor expansion valves, and the outdoor two-position valves. These are the only 4 parameters which can be sort of locked in or manually controlled during a steady state test. And these are the 4 parameters which we are observing or monitoring during the CVP. Beyond these 4 parameters, everything else has to be kept free floating, such that the manufacturer cannot lock that setting in, or the lab personnel cannot lock a setting in. You basically let all of those parameters just run on their own. Now, we had a lot of discussion. We in fact looked at the entire refrigeration cycle to see how which parameters are going to be the most important and critical for the purpose of CVP. And we came to these 4 because we realized that the other parameters, even though they might be critical, they may be indirectly impacted when we try to modulate any of these 4. And beyond that, we also realized that the other parameters, even though they might be critical, they are best to be left free floating, because the impact of those parameters on the overall efficiency and performance of the product may not be as much. And so this is another big step, or a major step, which is being taken in the VRF industry, which is how do we basically, add this CVP in. This has been added into the new version of HRI 1230. So just, as a side note, HRI standard 1230 was recently revised and was published. I think there's a 2021 version now, which is available on the HRI website. So, anybody can go ahead and download it from the website. And the CVP procedure is basically, as written, is currently existing in the HRI 1230 procedure. And most likely the global standard is going to copy the entire procedure as is, with some minimal changes and tweaks in order to accommodate systems which are sold around the world. This is again a very quick walkthrough of how the CVP works. I went through a very high level walkthrough of CVP, but if we were to get into in a more technical, in-depth level, I would just very quickly just walk through, these 3 specific graphs. The first graph over here that you see is basically a time length, or you could say a time duration of how a system, which has been a VRF system, which has been installed in a test chamber, would behave. And then the same sort of time duration applies to, how the compressor of that particular system will behave, and then how the indoor units of that particular system will behave. This was of course taken from HRS standard 1230, so which is why you kind of see the IP units, but I've kind of just added units over here for your reference. And just to very quickly get through, this overall walkthrough, the intention is that you would install a VRF system in a test chamber, and you basically don't touch it at all. And you simply just modulate the test chamber temperature, which is going to be your outdoor ambient temperature, basically. And that temperature has to be in a certain range, which is going to be 27.8 degrees Celsius and 30 degrees Celsius. So a manufacturer can choose whichever point that they want within this range that they want to start off the CVP at. And then we let the entire indoor test chamber to sort of run for a certain period at this particular temperature condition, such that we can get stabilization. So what you see over here is a stabilization period, such that the unit is basically getting acclimatized to the ambient temperature. In addition to that, the test chamber itself is making sure that the overall temperature in that chamber is uniform. While the stabilization is taking place, what's happening on the compressor side of things of this particular system, you're going to see like the compressor basically turning on and then basically ramping up, to the desired state, such that it will then after that basically stay the same as long as we don't really change the outdoor ambient temperature. And then at the same time, you're also going to see the indoor units, which will just all kind of turn on once the system has basically got enough time to react to the overall temperature. Subsequently, we're basically going to start ramping down the test chamber temperature. This is basically the R1 out here. The ramp down will happen until we basically get very close to the set point thermostat deadband. So if you're basically going to put your set point for this VRF system at 26.7 degrees Celsius, then you basically want, most likely your thermostat deadband would be, either, 1 degree Celsius or 2 degrees Celsius, or even 3 degrees Celsius. Whatever that dead band is, plus minus, you basically want your ramp down to be coming up right at the edge of that particular thermostat dead band. After that, you want to basically try to elongate on the temperature ramp down as much as possible, but within a certain within a certain range, such that you're able to get enough data and effective data in the best case possible, right? So the slower you make this ramp down, the more precise your data ratings can be. And this ramp down, the slow ramp down, will basically go on until a point when you're going to see your first indoor unit shut off. When your first indoor unit shuts off, is basically you've basically got a 60-minute period from that point on that your data ratings are going to be used for the purpose of the CVP. And I'll come back to this. Is probably going to be most important. Now, but after the point when the first indoor unit shuts off, you basically let the indoor test chamber temperature to ramp down until a point when all of your indoor units are turned off, which is perfectly fine. But this dark gray period is basically a 60-minute period prior to the first indoor unit being shutting off. That's the data that you're going to use and basically verify whether the manufacturer's reported or specified compressor speed, which are going to be used for the steady state test, or the manufacturer specified values, which are going to be used, whether it's compressor speed or outdoor fan speed, or even the expansion valve. These three specified values that the manufacturer wants to use for the steady state test, those have to be verified with what you kind of get in this gray area. There has to be a 3-minute interval such that the compressor speed, the fan speed, and the expansion valves have to be within a certain tolerance from what the manufacturer really wants to use. And if they are within the tolerance, then go ahead and use it. But if they're not within the tolerance, then you basically have to use whatever you found in this particular gray area as an average value for compressor speed, fan speed, and expansion valves, and then carry it over to the steady state test. So again, this is a very quick walkthrough of some of the details. Of course, as I mentioned, you can download the HRI 1230 procedure, which has a CVP in there. But of course, this is also going to be used or included in the global VRF standard. Another item which is going to be addressed in this global standard is performance mapping. As I mentioned, to allow for flexibility and to provide the end user with performance data which may be most relevant to their specific interest. We do need to kind of think about whether we can expand the ratings for VRF to beyond just standard ratings to application ratings, and those application ratings should then be basically verified as per this test procedure. And so we have included, the exergy-based performance method or performance mapping method. It's sort of loosely based on the data, which we see in EN 14825. There have been some tweaks which have been made for the purpose of the global standard. But the intent is that you will use your exergetic efficiency as well as your Carnot ER in order to come up with your ER performance map. And there are several assumptions which have been fed in, but those assumptions have been fed in based on careful review of manufacturers who are basically the subject matter experts of their equipment to see whether those assumptions would basically apply to their systems or not. Assumptions on your evaporating temperatures, assumptions on your condensing temperatures, and so forth. And eventually, these things will be provided in an addendum as to how to calculate step by step your condensing temperature map, your evaporating temperature map, and then subsequently your Carnot ER, and then subsequently your exergetic efficiency map, and then eventually, at the end, you will get basically your ER performance map. All of this will be basically, mentioned step by step in that particular addendum of the global standard. The intent is for the performance mapping approach to be applied to not just cooling, but also heating. Again, I think, for the purpose of the discussion in this presentation, I think cooling is probably going to be most relevant compared to heating. And I personally think this is going to be a dramatic improvement from how things are done today. When we look at other HVAC equipment, we do see that there is a provision for performance map, whether it's HRI 550, 590 or chiller space method. But I think it's about high time that we try to do this for VRF equipment as well. It's a bit more complicated, because in VRF equipment you have to look at not just the combination, a performance map of how it would work for an outdoor unit, but you also have to look at how the performance map works, for a combination of outdoor unit and indoor unit. And I think that has been sort of carefully thought through. A lot of meetings have happened, a lot of discussion among brilliant minds from a technical standpoint to actually get to a point where we are at today. Some other notable provisions which are also being added to the standard or the test procedure. One thing I would mention is that sound is a very important thing. We as population density grows, in major metropolitan cities, noise pollution and noise emittance has to be addressed, and which is why HVAC systems have to have sound ratings and a standardized method for measuring sound. And then eventually, of course, that will enable, the systems to be, competing for a lower sound level as much as possible. And to that point, we as a committee on the global standard looked at a plethora of sound test procedures which exist in different regions. I mean, we looked at ISO 13261-1 and -2. It has a very nice, accurate test procedure for sound, but it just doesn't apply for variable speed systems today. We looked at GIS, 8616 Annex D, as well as GIS 9815. Japanese standards, they do apply to variable speed systems, but the thing is that, it's hard to, or difficult rather, to access a GIS standard, in English. And, we wanted to make sure that we try to provide a test procedure which, folks or users from around the world are able to get easy access to. We looked at HRI standard 270 and 350, and those were very good, important candidates. And at this point in time, we have sort of tentatively agreed to proceed with EN 12102, which is the sound test procedure used in the European countries. That procedure does check a lot of boxes. It applies to variable speed systems. It has a broad enough decibel range to encompass various VRF systems from around the world. And it is relatively easier to access for users around the world, and it is in English, of course. However, as I mentioned, deviations for national regions for North America, I think there is going to be a requirement that we still use HRI 270 and 350 because there are local specification requirements on complying with 270 and 350. But the good thing is that most of these standards that I mentioned, their basis is all the same. Their test measurement requirements usually are more or less the same. They might have some variations between one or two, but I would say, at least like 3/4 of the test procedures remain somewhat similar to each other. And so it is easy for, let's say, a manufacturer, without having a major amount of testing burden, basically conduct the sound test, as per one particular standard, but then have, in different parts of the regions, if the requirement is, let's say EN 12102, then you can easily convert the data, the tested data, for the purpose of the standard and complying with it and the ratings that come out with it. And so I think, the sound is going to play an important role or an aspect in this particular test procedure. And as for the rating conditions for cooling, we're going to look at the 100% load at 35 degrees Celsius outdoor ambient temperature, which is usually, the worst case scenario for a system. And that's when the system might just be the loudest. And for heating, we're looking at a 7 degrees Celsius outdoor ambient at 35% load point. In addition, now, as I mentioned in the outline for this presentation, we also have been thinking about how to best support the various user community in regards to from building efficiency and building simulation standpoint. This is again like an area which is getting a lot of interest from around the world, and where the users, or I would say like various regions, are now looking at efficiency, not just from a component or an HVAC standpoint, but now from an overall building or a systems standpoint. What is the overall efficiency of a particular building? And so, there are some sophisticated and well thought through modeling tools or simulation tools which are currently being developed or have been developed already. And from a VRF standpoint, we decided to we discussed to see what would be the most appropriate way that we can help support this overall effort. And we came to a conclusion that if we were to basically provide data or publish data at a granular level and a segregated level, then that data can then be plugged into these modeling tools and simulation tools effectively, such that you get a more accurate rating from a building standpoint. And so from a if we were to look at it from a power consumption standpoint, the power consumption of indoor units, the power consumption of off mode, the crankcase heater, thermostat off mode, these are going to be now measured separately as per this test procedure. And then they're also going to be published separately if you were to comply with this test procedure. And the publication of those ratings, or I would say like these values from a power perspective, should now then help to effectively and accurately conduct, these modeling analysis for building efficiencies. Now, after, like, of course, we've gone through a lot of information, and we've taken a dive into several areas of the standard, but this table is just a very high level view of what kind of requirements are we kind of adding into this test procedure. And it is also to show that this is not simply just a compilation of various requirements from regional standards and then coming up with a big massive booklet. The intention over here is that, yes, we take certain requirements which have been best proven in certain regions, and then basically copy them into being used on a global scale, because we've learned from lessons learned. Well, we've had lessons learned. We've realized that they work effectively. So why reinvent the wheel? Why change something which is not broken, right? But in addition to that, the intention is that we are also thinking ahead, and we're thinking about what are the new requirements which should be added in order to accommodate, the issues of tomorrow, such as CVP, such as exergy-based performance mapping method, such as sound testing. These are somewhat new sort of requirements which don't exist in various regional VRF standards. And therefore, this is, of course, thought about as a step forward, with, of course, the support from one of the best minds coming in from a global perspective. Timeline. Now, we've been, as I mentioned, we've been hard at work for about a couple of years now. And we are at a stage where the draft is nearing completion. There's still some work to do, but we're, to be honest, Henry's team is setting up almost daily meetings, between a smaller group, just to basically accelerate the development process. And really appreciate, the entire committee's dedication and hard work to get us to a point such that we basically have a first draft ready by Q2 of 2021. So, perhaps in a couple of months, within a month or two rather. Once we have this first draft ready, it's going to go through a review process, within various stakeholder groups, so a much larger group of the VRF Global Standard Committee will take a look at the standard. There might be some testing which will be conducted to verify that the requirements that we're adding in are in fact okay and acceptable. And so, we will come to a point where the final draft, or rather, I wouldn't say really a final draft, but really a draft which could be finalized for additional review or a broader review should be ready by Q3 or Q4 of this year. And at that point of time, we expect that this draft standard is going to be presented to ISO as a new work order item. And there probably is going to be maybe a new, a technical committee or a TC under ISO, which will be formed to review, the work that has been put into this global standard, as well as the draft, and then carry it forward through its review process and all the way to publication. So the intention is to publish this through the ISO platform, such that we get a much broader outreach as well as acceptability. And once it is, of course, published, in sometime in Q2 of 2022, is when I think there's going to be some efforts to push this for local adoption in regions and countries which are looking into adding a new test procedure or rating method for VRF equipment, or even in countries such as US and in Europe, or regions such as Europe, to have this standard be used as perhaps the next revision cycle for their national adoption. And we also understand that there's a lot of work that needs to be done for manufacturers to comply with the standard. There's just too many requirements and too many caveats which have to be met, and therefore we expect that it will be after 2023 when we're going to see the actual publication as well as the adoption of this test procedure from a manufacturing standpoint, to conduct to conduct testing and to start working on ratings. And the regional adoption will also vary, so in certain regions which may be ready to adopt this global standard right away, they might go ahead and adopt it, right after 2023. But then for certain other regions, there might be either regulatory requirements or there might be, some other issues which may not enable those regions to adopt the global standard right away. And so therefore, I think this will still remain as a reference document that can be used once, their specific timeline opens up to take a look at the VRF standard. And of course, this presentation on the progress of the overall test procedure and the rating standard is one of the first presentations that we're making publicly. We do anticipate that once the draft is in presentable stage and at a stage where a lot of the requirements have been sort of at least vetted through, so when we're going to go ahead and just open it up for public review. And I'm going to be very happy and glad to receive any feedback and comments that we can get on that test procedure, such that it can then be eventually taking into account things that might not have been thought about properly or thoroughly, and just make sure that there might be some specific requirements that have to be added in or modified into this overall test procedure. So I think that turned out to be one of the last slides that I had. So I'll basically go ahead and take a pause, drink a glass of water, and pass it on to Ashish or Henry, if there's anything else that you'd like to add, or what are the next steps in general for this presentation.
So thank you, Ruchi. I think maybe another few minutes. Oh, yeah. So you're handy with the bottle. So
yeah, all good.
Okay. So I would request all the attendees, if they have any questions, that they can put here, and we'd like to take them right now. There are a couple of questions that, if you are okay, we can just ask you right now.
Sure.
So one of the questions is that what is the rationale of using 27 degrees centigrade as the indoor bulb, dry bulb temperature, whereas nowhere it is kept as a thermostat set point? Even if various ISO standards use this value, why no one is attempting to get this close to realistic value? Using a higher indoor temperature gives undue advantage to manufacturer as the evaporator heat exchanger operates against a higher delta T, thereby increasing the effectiveness of the heat exchanger. Part two of the question is what order of COP and capacity decrease is expected if 27 degrees C is reduced to 24? So if you can take this.
Yes, of course, and that's a great question. So credit to whosoever came up with this question, but and I completely agree. With the rationale that was at least provided regarding the efficiency that you can get at 27 degrees Celsius versus what you would get at a lower indoor room condition. Of course, if you lower the temperature from 27 degrees Celsius to, let's say, 23, you're probably going to reduce like levels of efficiencies as well. Yeah, completely understandable. Now, I think 27 degrees Celsius just has been in all of these standards historically for decades. I mean, I think even before some of us on this call were even born. And I think from what I understand is that there was a mixture of outdoor air with indoor, which was taken into account. And then eventually it came to a conclusion that 27 degrees Celsius may be more appropriate. Now, there might be regions around the world which might say like 27 degrees Celsius is still okay or acceptable. But I agree that majority of the regions, will state that, maybe perhaps 23 degrees Celsius or maybe around that range or value may be more appropriate. It's just that currently, if we were to go ahead and reduce 27 to another temperature, anything that if we were planning on using or leveraging in terms of current test data, measurement data for the purpose of this global standard, that can no longer be done. And which basically, increases the burden, or you could say like the work on the manufacturers to develop the ratings by tenfold. And therefore, the intention is really to keep it at 27 degrees Celsius, at least for the first iteration, or we could say the first version of this test procedure, such that we can then at least provide some additional time to the manufacturers, as well as the other community within the VRF world to work on the ratings as well as testing as per a lower indoor dry bulb. And then subsequently, I think we will then be ready to go ahead and lower this indoor dry bulb temperature. But my personal opinion is that I think we're going to see at some point, down the line in future, that this temperature, from 27 is probably going to be reduced to something which should be more representative that we see in the field. Completely get the point. So.
Yeah, I think so. The question came from Mr. Jyotirmay Mathur, and I don't know if you would have had the, the right to, speak. He would have not let this thing go easily. So probably on his behalf, I would say that when we are making the effort and we do realize that 27 is not the correct benchmark, I'm like, why do we wait for second iteration when we are doing so much of an elaborate work to put the global standards put together? Why start with something which is, not real perfect ab initio? So anyways, that is probably, he would have said, so he says the point. Yes, exactly, Ashish. So maybe.
So I have a suggestion. Why don't you unmute Mr. Jyotirmay Tapasji, and so that he can have a one-to-one interaction? Is that right, Ashish? Won't it be a good idea to unmute Mr. Jyotirmay?
Yeah, I think, sir, I would love to do that. And there's only one more question which is here. So in the time that, Tapas is going to make that arrangement, I will quickly take the other question. Okay. And so we'll come back again to Jyotirmay ji. And the other question, let me see. Yeah, so it says, what is the difference between CZ1 8 and CZ0.
Oh, right. So the climate zones 1 through 8 and climate zone 0, these are, you could say, buckets which have been developed or established as per ASHRAE 169 standard. ASHRAE 169, talks about the different temperature profiles or climate profiles, around the world. So climate zones 1 through 8 may represent a different climate profile for that matter. So as I mentioned, climate zone 0 is, let's say, hot and humid climate, right? Very hot and humid climate. 1 maybe just simply hot, right? And then climate zone 8 may be on the other side of the spectrum, which is maybe, very cold climates for that matter. So the intention is that, at least for climate zones 1 through 8, the conditions that we see on the screen can be applied without much deviation. But then I think from climate zone 0 perspective, usually it becomes a problem because if your full load testing is happening at 35 degrees Celsius, you're basically going ahead and extrapolating that data to come up with 46 degrees Celsius to see what might happen in the East. And is that really a full accurate representation or of the method that needs to be used for getting those ratings and verifying those ratings? And that's where I think people are a bit skeptical about just having climate zone 0 condition equipment be kind of fed under climate zones 1 through 8. And so climate zone 0 sort of does require its own rating condition and bucket of, and climate zones 1 through 8 seems like, the representatives don't really have an issue in having those clubbed together. So, but again, the information on what climate zones 1 through 8 are easily found in ASHRAE 9. And I'd be happy to provide some additional information after the presentation.
Great, thank you. And there was one request we received for sharing the presentation. So I don't know, I think for viewers at large, if there is anybody who needs to have something more on this, this.
Richie, I have one more question for you. In
Yes.
these rating conditions, why have we not considered the wet bulb temperatures?
Well, so yeah, I mean that's again a good point. I think that has to be addressed at the global standard level. Yes, we did add the wet bulb on the indoor side, but definitely I think from the outdoor side, at least we need to have a discussion as to whether we need to have a wet bulb temperature or not. So
it's going to make a very large difference on the performance of the unit. The energy consumption's pattern will change with higher humidity levels. So this is going to be misleading, in areas which are going to have high humidity levels. Maybe a medium, let's say 35 degrees dry bulb, wet bulb temperature being small, there the machines are going to perform better vis-a-vis, somewhere else. So I think incorporating that wet bulb temperature is going to be critical once again while evaluating the performance of these machines or rating of these machines.
No, I completely agree, and I think we need to add in at least have a discussion about how to deal with the wet bulb on the outdoor side.
I don't know, Tapas, if you have been able to connect Mr. Jyotirmay, let me know.
Yes, I'm there.
Oh, okay. So great to. Oh, I can see you now. I'm sorry I missed you before. Great. So I think it's about time for me to mute myself, and I would, it's okay. Please go ahead, Mr. Jyotirmay, please.
So Ashish, first of all, there was a question about climatic zone. Richie already shared that most of the Indian cities, they are climatic zone 0. It is basically cooling degree day and heating degree day based classification. Somebody who's interested can refer one publication in ISHRAE journal, wherein we had calculated these values for each of the Indian cities for which weather files are available, and we had given a belonging of which city belongs to which climatic zone, 0, 1A, 1B, and so on and so forth. So just a piece of information. I think it was published about 2 years back. And if somebody needs, I can share that publication as well. Richie, coming back to this, first of all, you would be aware, and definitely Henry Wong knows that, we have met so many times, that there is a ISHRAE standard also for VRF. So, I mean, did you refer that as well while reviewing a lot of global standards, European, Japanese, and Chinese and all? Did you refer that? Because I didn't hear a word about that in the entire
No.
presentation.
Absolutely. I think that's a good question, Dr. Mathur. So first, we have not had, I think, access to the Indian global standard at this point, at least from a committee standpoint, but we would be very happy to review the latest draft of the Indian standard and see how we can add in requirements, which have been excellently might have been put into this draft standard and carry them over into the global standard. I think this particular presentation, one of the reasons of doing this presentation is so that at least like we open up on what's happening on the global standard front, but also get your feedback with respect to, how we can basically accommodate, certain issues or requirements which might be coming in from the Indian standpoint. And I think, yeah, Dr. Mathur, I think we as a committee need to, if possible, it would be great if we can get access to the global standard, the draft standard from India, and also basically any feedback along with the draft standard as to how, what needs to be added into the global standard. I guess have the two versions marry. So
yeah, I'll make sure that we send a copy of that. I think Henry would have that anyways, but still I will send it again. So one major concern which I always have, and especially somebody also pointed out in the question, is the effect of humidity. Many Indian cities are there where the ambient temperature is somewhere close to 25, but the relative humidity is very high. If I go by the load line, as per this standard, 25 degrees centigrade is corresponding to 47% of load. Whereas in a city like Mumbai, you may have 100% load at 25 degrees centigrade ambient temperature also. Okay. So that makes the testing irrelevant. So how the global standard is addressing such situations and trying to bring the test values close to the field performance of the systems?
Yeah. So how is the Indian standard handling it at this moment, the relative humidity requirement?
In Indian standard, the ICER value is load based. We had calculated load bins instead of temperature bins. So the temperature bins value, the temperature bin approach, which initially was there in many standards, is kind of neglecting the effect of humidity. So in Indian standard, we had calculated load bins using simulation of actual buildings, and then using those we had determined the weightages of A and B and C and the conditions, outdoor conditions corresponding to A, B, and C. So it was based upon the simulation, and then those conditions are kept instead of only the dry bulb based upon this linear value.
No, so I mean, again, Dr. Mathur, I think that's one of the things that like the global standard needs to take a look at, because or at least like have a discussion upon, because I think like the relative humidity requirements, which might be in the global standard, or at least if there are any, might not be representative of how things might happen in India. And I think using the Indian standard, or at least the approach, might be feasible. So at least I'd be happy to just take a look at it in more detail and provide some input or feedback back to the global committee members. So fully agree again on that point. And the other thing that you, sorry, go ahead.
No, please go ahead. I'm sorry. I'll speak later.
Yeah, and again, like I think and the same thing would apply to, let's say, the issue about the indoor dry bulb, which is 27 degrees Celsius. If there's a way that, we can sort of look at another indoor dry bulb temperature from 27 to maybe even 23, I think we need to assess the impact on the efficiencies, the impact on the work. But yes, if there's a way that we can kind of make that happen right now in the first iteration itself, then I think, yeah, we should definitely do that. So need to run this by the committee again within the global standard and see, we'll be happy to, whether there's a possibility and feasibility of reducing 27 to perhaps even 23 or 22. But please let us know if you think that there is a temperature profile, as well as maybe, this approach of addressing relative humidity through load bin fractions, which will be more representative of how the systems are today. And I think we can at least like still, change the direction of the standard to some extent.
Sure.
There is one thing, Mr. N. Suresh, I think so. Let me just check the name correctly. N. Suresh Babu, please, I request if you can, put your question on the chat box or on the Q&A. And there's another question which comes from another very revered gentleman, Mr. Tapan Basu, and he says, are we thinking of doing anything about water-cooled VRF standards? Is something happening on that?
Yes. I think there are select manufacturers right now which have water-cooled VRF offerings in the marketplace. And we're going to see water-cooled systems become more and more important, especially in densely populated cities and maybe like cities next to the coastal areas where you can actually use like, at least the ground source or even like, just use like the abundance of water around. But in general, yes, the intention is to keep away from having water source VRF equipment in the scope of the standard to begin with, because I think we're still trying to tackle a lot of other issues. And if we can tackle those issues in the first iteration, then I think we can come back to expanding the scope to water-cooled systems, and then also perhaps even to systems which are, beyond just, that 12 kilowatt threshold, whether we can go down on the residential side of VRF systems as well. The other things to note is that, today we might see like an uptick of VRF condensing units being installed with evaporators, which may not be from the same manufacturers, through EEV kits. So I think we need to like take a look at in the next iteration about how do we include those in the scope such that testing through EEV kits and ratings which come through EEV kits with a combination of other indoor units versus these outdoor units, are those going to be included in the scope or not? So still a lot of things that have to be kind of expanded upon, if not in this iteration, then in the next one.
Yeah, so there is another question. I don't really think it pertains to the standards, but it's a question, it's a generic question which says, can we use the VRF units in server rooms? So maybe I can let Mr. KD Singh answer this question.
Well, it's if you go typically for a server room and you want to have an accurate control on temperature and humidity both, then probably a VRV will have to go through some modifications, or we'll have to get in some additional controls to get that. So it all depends on the kind of the server room that you're trying to build there. Surely, in server rooms that have based themselves only on temperatures, probably the VRFs have worked very well. There's not been a problem. Small server rooms. But if you go to a data center which needs closer control on temperature and humidity and quality of indoor air, etc., maybe we might have to move to a higher version of a machine, which can control both temperature and humidity. VRF by itself cannot do this unless and until we do something from outside with the indoor units, or we have an air handling unit where we can build in some controls. A tailor-made air handling unit with the VRF outdoor unit can possibly do this. But then generally, I would say that if it's a data center or a VRF room which needs close control on temperatures and humidity, it's better to go for a precision air conditioning machine. I hope I've answered that. Richie, you can take it over, and if Jyotirmay sir is there, he can also answer that. That's what I would say.
I think KD sir, it's you've been very explicitly on the correct, taking thought in the correct direction. Actually, that's what I would say.
Perfect answer.
Yeah,
I agree.
So I have one question for Richie.
Yeah,
Yep.
please.
So Richie, now there are VRF manufacturers who manufacture different kind of VRFs. Some who manufacture only cooling machines. There are some manufacture cooling and heating, but there are either or option. That is, you can use it on cooling or you can use it on heating. And there are some manufacturers who go ahead whose machine you can use both for heating and cooling, right? Now, each of these machines will tend to have, separate COPs, as, when you're coming to the heating and cooling simultaneously. If you're using in a zone, which has a large daily range, like, in Kathmandu or Nepal, or maybe for a hospital where you need heating and cooling simultaneously, So how will the rating standards, rate these machines? Will you have separate rating standards for only cooling, separate heating standards for only heating, and then you'll have one for heating, cooling simultaneously? Or how will these rating standards how will they be made?
Yeah, so a great question, Mr. Singh. So I think right now I agree. Of course, you've got like just the VRF ACs, right, which will basically provide you cooling efficiencies. Then you've got VRF heat pumps, which will have the ability to do cooling as well as heating. And then you've got VRF heat pumps with heat recovery, which can do simultaneous cooling and heating. These have to be put into different buckets. In essence, of course, it all depends on the operability of the condensing unit. If the condensing unit is basically a heat pump, and if you do add in the heat recovery module to the heat pump, then you should be able to expand on the testing as available from the test procedure. So there is going to be provision for, just measuring the cooling side of the overall system, which is basically you go through the cooling conditions. There's a provision on the heat pump side. So basically you'll have to do cooling as well as heating conditions or test in accordance with cooling and heating conditions. And then for simultaneous cooling and heating conditions, there's going to be consideration of adding in another metric, which is the simultaneous cooling and heating efficiency, or SCHE in short, in where it's going to look at the performance of your heat recovery module. Now, we've also discussed on what should be the percentage of the number of indoor units operating in cooling versus heating at the same time, and whether that's going to be representative of the field. I think today in the HRI 1230 standard, and this is something that we caught really late on, is that we basically put 50% of the indoor units in cooling and then 50% in heating, and then we run a test. But that's not really representative of what we probably want to see in the field, because technically, you might have like 25% of your indoor units which might be in cooling and 25% in heating, and then the rest might just be even shut off. So I think we've looked at like different variations of like what should be a number of indoor units which need to be in cooling, number of indoor units which need to be in heating, and within those, how many indoor units need to be inactive, right? Like, so yes, I agree with you. It's going to be complicated because we're adding in further layers, how the AC might work versus a VRF HP versus a VRF HP with heat recovery. But there are provisions which are going to be in the standard in regards to how these be calculated. And then subsequently, there will also be, I guess, another efficiency metric on calculating the simultaneous cooling and heating nature of these systems.
Yeah, I think the whole idea, I think, is about to creating a benchmark where rating can be done, and field situations will be always be dynamic, and I don't really see any standard which will be able to handle 100% of situations. But at the same time, I think these are points that come to the table, and these are food for thought and for your committee to deliberate upon. And I think we will kind of arrange Mr. Jyotirmay Mathur to send you his the Indian standards that we have done at ISHRE. We'll share a copy with you. Again, I would like to extend a really big thanks to AHRI team, Henry, for making this presentation happen, and then recommending Richie to you, and Richie for you to taking time out to be with all of us, and taking all our concerns and questions. I do hope that we will get some more questions, and we will directly post to you for your personal reply. And we look forward to further more interactions with AHRI and building standards which would be universal to even to India in the way we think about it. So with that, we close this session. Thank you so much. Thank you, KDG. Thank you, Richie. Thank you, Henry. And thank you all the attendees for being here with us today. The show is closed. Thank you.
Thank you. Thank you, everybody. Thank you, Richie, and thank you, Henry. Thank you, Ashish ji. And it was wonderful, Richie. I think it was a great presentation. So I think there's lots of things that we will take offline and discuss, but I think it set me thinking. So that's what I can say personally, that I really enjoyed it. So thank you very much for being here, and thank you for having spared time to to have help all the DCI and the ISHRE members to enrich themselves. One of the very interesting and I think the most sought for subject now, the VRFs. So I think so. Thank you very much. Thank you.
Thank you. Thank you, everybody. Thank you.
Thank you, sir. Thank you very much.
Thank you.
Should we close this session now, sir?
Yes, please. Thank
Yeah.
you.
Okay.